Well, we shall in this lecture continue what we had started in the last lecture. In the previous lecture, we had studied or learned some preliminaries about studying the spectral properties of graphs. We had defined the adjacency matrix and we had observed some of its properties. Like we had seen the trace of the adjacency matrix is always equal to 0. That was the first observation. And then we had also seen that the sum of all 2 cross 2 principal minors, that is minus times or negative times the number of edges in the underlying graph. And then we had also seen that the sum of all the 3 cross 3 principal minors is twice the number of triangles. So before starting more about the spectra of these graphs, we shall have a little review on what we had done in the previous lecture. So first we had defined that AB, the adjacency matrix of a graph, of a graph. So then the first observation was trace of A is equal to 0. And in fact, all the diagonal entries of A are equal to 0 because our underlying graph will always be a simple graph, that is a graph without loops and parallel edges. Now, the second observation was the sum of all 2 cross 2 principal minors. The sum of all 2 cross 2 principal minors is equal to negative times the number of edges in the graph. So it is minus times the cardinality of the edge set, minus times the size of G. Now, the third observation was the sum of all 3 cross 3 principal minors. The sum of all 3 cross 3 principal minors, this was twice the number of triangles. Twice the number of triangles in G. Okay, then we had defined the characteristic polynomial of a graph. So characteristic polynomial of a graph, characteristic polynomial of G. This was denoted by P, or in fact we had denoted it by C, G, lambda. And now this is defined to be the determinant of A minus lambda I. That is the characteristic polynomial of this adjacency matrix A is defined to be the characteristic polynomial of the graph G. And then we had defined what we mean by the spectrum of G. And spectrum of G is the set of all eigenvalues of G together with their multiplicities. So if the eigenvalues are, suppose the distinct eigenvalues are lambda 1, lambda 2, lambda k, then suppose the arithmetic multiplicity of lambda 1 is equal to m1, then we will write this lambda 1 power m1 in the spectrum, and similarly lambda 2 power m2 and lambda k power mk. Or we can also you also write the spectrum of a graph in this permutation form. We write the eigenvalues in the first row and we write their multiplicities in the second row. So here it is m1, m2, and mk. So these things we had discussed in the previous lecture. Now we will take some more observations that we had not taken in the previous lecture. So if G is disconnected, if G is a disconnected graph, if G is a disconnected graph, having the components, having the component is G1, G2, so on, G, suppose T, having T components, then we can put the adjacency matrix of G in the form. So how we can write adjacency matrix? It is like this. The adjacency matrix of G. This can be write like this. So first we can write here the adjacency matrix of G1. Then the next diagonal block will be the adjacency matrix of G2 and so on. And here we can write the adjacency matrix of GT. And all the remaining entries of this graph is equal to 0. So everywhere we have 0 except the diagonal entries. In fact, they are the diagonal blocks. So therefore, if we have a disconnected graph having T component as G1, G2, GT, then the adjacency matrix of this G can be put in this kind of a block matrix form. So then the characteristic polynomial, of G can be put in the form. So in fact, from this block diagonal form of this A of G, we can write the characteristic polynomial of G as CG lambda. This is equal to the determinant of A minus lambda I. So, or since we have to highlight here what is this A, so it is A G minus lambda I. Now, this is in fact equal to A G1 minus lambda I, then determinant of AG2 minus lambda I, and so on, the determinant of AGT minus lambda I. Then with this observation, we shall only consider the connected graphs. So since if we have a disconnected graph, we can put the characteristic polynomial in this form. So it is better to study the spectral properties of connected graphs. And whenever then we have a disconnected graph, we can easily study the spectral properties from this equation. So from now, we have already taken this G to be a simple graph, but now because of this observation, we shall now onwards take this G to be a connected graph, connected as well as simple, unless otherwise stated. So thus in our study, of spectral properties, thus in our study of spectral properties of graphs, we assume the graph G is connected. So from now, we will assume our graphs are simple, connected graphs. Now, before taking some examples of how we how we evaluate the eigenvalues of some spatial kinds of graphs, we shall take this spatial kind of a matrix that has to be used then. So let's call it a proposition. And in this proposition is like the eigenvalues of Jn, where Jn is an n cross n matrix whose all entries are equal to 1. The eigenvalues of Jn are n power 1 and 0 power n minus 1. So by this power, we mean that this Jn has only two distinct eigenvalues. One is n and another is 0. One is repeated just one times and 0 is repeated n minus 1 times. So that's in the notation of our spectrum, that is spectrum of this matrix Jn. This is equal to n, 1 and 0, n minus 1 times. So now in the proof, so clearly, rank of this Jn is equal to 1. And this can clearly be seen if we have n rows in this Jn matrix, then we can take R2 minus R1 gives R2, R3 minus R1 gives R3, and similarly Rn minus R1 gives Rn. In this way, in just immediately in one step, we will see that the new matrix so obtained will have just to first row a non-zero row, and all the remaining 0 rows will be made into 0. So therefore, the rank of this Jn is always equal to 1. Now, since this Jn is a symmetric matrix, now Jn is a symmetric matrix and having rank 1, now Jn is a symmetric matrix and has rank equal to 1 and has rank equal to 1. So thus Jn has exactly one non-zero eigenvalue. In fact, here we don't need this symmetric property of Jn, just that the rank of this Jn is equal to 1. It itself guarantees that there is exactly one non-zero eigenvalue. Now since trace of Jn is equal to n, because all of the diagonal entries are equal to 1, so trace of Jn is equal to n, but we know this is equal to the sum of eigenvalues. But since exactly one eigenvalue is non-zero, and all the remaining eigenvalues are equal to 0 because the rank is equal to 1. So thus, the only non-zero eigenvalue of Jn is n. Hence, therefore, now since the remaining eigenvalues are equal to 0, and since this Jn is an n cross n matrix, so it has n eigenvalues, one of them is 0, and the remaining n minus 1 will be equal to 0. 1 is n and the remaining n minus 1 are equal to 0. So therefore, spectrum of Jn, it is n, an eigenvalue repeated 1 times, and 0 is an eigenvalue repeated n minus 1 times. Or we can also write it, it is n power 1 and 0 n minus 1 times. Now we take our first result about evaluating the eigenvalues of the graphs. So let's take it in the form of a theorem. For any positive integer n, for any positive integer n, the eigenvalues of the complete graph, the eigenvalues of a complete graph, the eigenvalues of a complete graph Kn are n minus 1 once and minus 1 n minus 1 times. So that is spectrum of a complete graph Kn. This will be equal to spectrum of the adjacency matrix of Kn. Now this is equal to one of the eigenvalues is n minus 1 and it is repeated just one times, and all the remaining eigenvalues are equal to minus 1 and they are repeated n minus 1 times. Or we can write this thing as this is n minus 1 once and minus 1 n minus 1 times. So let us do the proof. Now by definition of a complete graph, since there is an edge between any pair of vertices. Now, if we look at the definition of the adjacency matrix, we have a 1 as the ijth entry if the vertices I and j are adjacent to each other. Otherwise, we have 0. So clearly, the adjacency matrix of Kn has 1 at every non-diagonal position, and all diagonal entries are equal to 0. And all diagonal entries are equal to 0. So thus, adjacency matrix of Kn, this can be written as the J and n cross n matrix minus the identity matrix of order n. So this clearly comes from the definition. Now, any two vertices in a complete graph are adjacent. So if we take any non-diagonal entry, that will be corresponding to some two vertices Vi and Vj. So that Vi, Vj entry, that will be equal to 1 if I is not equal to j, and if I is equal to j, then that entry will be equal to 0, because we know that the diagonal entries of adjacency matrix are always equal to 0 because this Kn is again a simple graph. So in the adjacency matrix of Kn, all the non-diagonal entries are equal to 1 and all the diagonal entries are equal to 0. And this adjacency matrix of Kn can be then verified to be equal to Jn minus In, because when we evaluate this Jn minus In, Jn has all of its entries equal to 1. Now we are taking minus In. So that means when we evaluate this equation Jn minus In, we get 0 at the diagonal entry of this Jn minus In, and all the non-diagonal entries of Jn remain invariant under this minus In. So therefore, this Jn minus In is the matrix, adjacency matrix of the complete graph on n vertices. Now here, in order to evaluate the eigenvalues, we will use the eigenvalues of Jn, and also we will use the spectral mapping theorem. The spectral mapping theorem states that if, so let's write the statement of the spectral mapping theorem here. Spectral mapping. So it maps the spectra of a matrix with something else. So what it means, if f of x is a polynomial, if f of x is a polynomial and A is a matrix with lambda as its eigenvalue. With lambda as its eigenvalue, then the spectral mapping theorem states that f of lambda is an eigenvalue of f of A. Eigenvalue of f of A. The eigenvalue, so therefore, if A is any matrix and f of x is a polynomial, then f of A is a polynomial, it is a matrix polynomial. So if lambda is an eigenvalue of A, then corresponding to this lambda, f of lambda is an eigenvalue of f of A. And in fact, from the proof, it can easily be seen that lambda is an eigenvalue of A, f of lambda is an eigenvalue of f of A. Now, if x is the eigenvector corresponding to A, now if x is the eigenvector of A corresponding to lambda, then the same x is the eigenvector of f of A corresponding to f of lambda. So in fact, we have this equation. In fact, if Ax is equal to lambda x, then f of Ax is equal to f of lambda x. So this is the exact statement of the spectral mapping theorem. So here we know what are the eigenvalues of Jn, as we have done in the previous proposition. The eigenvalues of Jn are n once and 0 n minus 1 times. And also we know what are the eigenvalues of In. They are 1 taken n times, and all the eigenvalues, in fact, of In are equal to 1. So then using the spectral mapping theorem, and proposition we have the eigenvalues of adjacency matrix of Kn, which is equal to Jn minus In R. It is the eigenvalue of J n minus an eigenvalue of In. So the first eigenvalue will be equal to n minus 1. The next eigenvalue will be equal to 0 minus 1. Then again 0 minus 1, and so on, 0 minus 1. So that is spectrum of Kn. This is equal to n minus 1, which is once an eigenvalue, and then minus 1, n minus 1 times. So with this, we completely determined what are the eigenvalues of the complete graph Kn. Now we will discuss the eigenvalues of the complete bipartite graph. So in the next theorem, so now theorem number 2. The eigenvalues of a complete bipartite graph. Complete bipartite graph Kmn are square root of mn, negative square root of mn, and 0 m plus n minus 2 times. So that is spectrum of Kmn. This is equal to square root of mn, and this is 1 times an eigenvalue minus times square root of mn. This again 1 times an eigenvalue and then 0. And this is an eigenvalue m plus n minus 2 times. Now let us do the proof. From the matrices of graphs, we can easily see that how we can construct the adjacency matrix of Kmn. The adjacency matrix of Kmn is it has actually this special kind of a C shape. Its adjacency matrix of A Kmn, which is equal to A Kmn. This has this kind of a shape. So here we have 0 matrix. Then here we have a matrix J of order m n. Or we can write it like this. Here we have a matrix of order m. Here we have a matrix of order n, and here we have 0. Now, since this Kmn, this has m plus n vertices, so therefore its matrix will be a adjacency matrix will be a matrix of order m plus n cross m plus n. Now, since this J m it's a square matrix of order m cross m, this Jn it's a square matrix of order n cross n. So this whole matrix is a square matrix of order m plus n cross m plus n. And earlier we have also seen that the eigenvalue, what are these eigenvalues of Jm and what are the eigenvalues of Jn. And in fact, we have also seen that the rank of this Jm is equal to 1 for any value of m. And so obviously, the rank of this Jn is also equal to 1. So once we have rank of Jm is 1 and rank of Jn is 1, that means the rank of adjacency matrix of the complete bipartite graph Kmn, that is equal to 2. Now, so since rank of Jt is equal to 1 for all t greater or equal to 1. So thus, rank of adjacency matrix of Kmn, this is equal to rank of Jm plus rank of Jn. Now rank of Jm is equal to 1 and rank of Jn is equal to 1. So rank of the adjacency matrix of Kmn is equal to 2. So once we have rank of this matrix is equal to 2, so thus this
it's 7 o'clock.
Adjacency matrix of Kmn has precisely 2 non-zero eigenvalues. Non-zero eigenvalues. Okay. Now so now we will make one more observation in the adjacency matrix. Now, since trace of this adjacency matrix A is equal to 0, and we have exactly 2 non-zero eigenvalues. Thus, these non-zero eigenvalues are precisely of the form of the form lambda and minus lambda, because we need the trace to be equal to 0, and we know that the trace of a matrix is the sum of its eigenvalues. But since we have the rank of this adjacency matrix of Kmn is equal to 2, so it has precisely 2 non-zero eigenvalues. But now, since the sum of all the eigenvalues must be equal to 0, so these two non-zero eigenvalues must have the form lambda and minus lambda. So they must be the negatives of each other. So therefore, we have two non-zero eigenvalues for this Kmn. And in fact, we have completed showing that it has 0 as its eigenvalue taken m plus n minus 2 times. But now we need to show that this lambda is equal to square root of mn, and minus lambda is minus times square root of mn. Now we have already observed that, but since the sum of eigenvalues, now since the sum of eigenvalues of a matrix taken two at a time, is equal to the sum of all 2 cross 2 principal minors. Now this is an observation from the matrix theory. The sum of all 2 cross 2 principal minors is the sum of all eigenvalues taken 2 at a time. So sums of products of eigenvalues taken 2 at a time. So it's actually the sum of products of eigenvalues. Sum of product of eigenvalues. Product of eigenvalues taken 2 at a time is the sum of all 2 cross 2 principal minors. So actually this left-hand side can be written, it is equal to, this is something like, if alpha 1, alpha 2, alpha n are the eigenvalues, then this sum of products of eigenvalues taken 2 at a time can be written in this way. This is alpha 1, alpha 2 plus alpha 1, alpha 3 plus so on, plus alpha 1, alpha n plus alpha 2, alpha 3 plus so on, plus alpha 2, alpha n plus so on, plus alpha n minus 1, alpha n. That is the sum of all sums of products of eigenvalues taken 2 at a time. This sum is actually equal to the sum of all 2 cross 2 principal minors. Now, so thus, sum of all 2 cross 2 principal minors is equal to sum of products of eigenvalues taken 2 at a time. Now, since this adjacency matrix has precisely two non-zero eigenvalues, they are lambda and minus lambda, and all the remaining eigenvalues are equal to 0. So if we evaluate this equation, alpha 1, alpha 2, alpha 1, alpha 3, so on up to alpha n minus 1, alpha n, we will get just one non-zero term, and that non-zero term will be lambda into minus lambda, that is minus lambda square. So this sum of all 2 cross 2 principal minors, so this can be equal to, so now this is equal to minus times lambda square. But now in the previous lecture, we had observed that the sum of all 2 cross 2 principal minors is negative times the number of edges. So this implies minus times the cardinality of the edge set of Kmn. This is equal to minus lambda square. So this implies the order of the edge set of Kmn. This is equal to lambda square. But now since Kmn is a complete bipartite graph, with one vertex set having m vertices and another vertex set having n vertices. So we clearly know that the number of edges in a complete bipartite graph of this form is equal to m into n. So this implies m into n is equal to lambda square. And this equation implies lambda is equal to square root of m into n. So in fact, positive square root and the negative square root. So this completes, so thus spectrum of Kmn. So this is equal to this square root of lambda, square root of mn, this is an eigenvalue 1 times, then minus lambda, that is minus times mn, this is ones, and all the remaining eigenvalues are equal to 0. So it is m plus n minus 2 times. So this is the spectrum of the complete bipartite graph Kmn. So we shall stop here in this lecture. Thank you so much.